All right, hello everyone. I'm Andrew Toivonen and I work with Michael here at University of Minnesota.
And I'm Emily Foley. I'm a junior undergraduate at Wake Forest University. I'm interning here for the summer, working with these folks.
So we're going to be talking about gravitational wave data products and observing scenarios. So pretty much everything after a detection is made. It's going to be in the way, I can hide these. All right, so first we're going to talk about the gravitational wave data products. And first we need to talk about motivation. Why do we care, right? So one of the main areas of study is a neutron star. What is it made out of? And what is the equation of state of a neutron star? And when we talk about equation of state, we're talking about what physics define the way that a neutron star works, essentially. One of the main things is how, what you could say, stiff a neutron star is. So when the gravitational forces of a merger come in, how much does it stretch? Or how brittle is it, right? Is a lot of mass going to break right off? Because that's actually a lot of what we care about, is how much mass is going to be ejected from that merger, called the mass ejecta. And that mass ejecta is directly related to how bright the kilonova will be, if there is one, because that's essentially the matter that's going to be undergoing this R process nucleosynthesis, which was introduced already, I think, in one of the first talks. And that's a whole bunch of nuclear reactions that are going to release a whole lot of energy. And that's one of the main driving forces of the kilonova that you'll see. And that brings us to the last one, a kilonova, which can only result from a binary neutron star or an NSBH. We'll have better odds with the binary neutron star because, again, we're looking for mass ejecta. So if we're talking about a binary neutron star, we're more likely to have mass ejecta. If we have an NSBH neutron star and a black hole, the black hole can kind of just swallow up one of the other ones, the neutron star, and you don't end up with a big chunk of mass ejected that can undergo all the nuclear processes and lead to that kilonova. And so now that we've talked about why we care, what are some of the things that we measure or try to measure? So we're talking about after, let's say, the detector, at LIGO or Virgo, we've made a detection, and we now want to try and estimate what did we just detect. So initially, things like M1 and M2, the component masses, what are the two masses, and then the mass ratio, obviously, which goes directly from that, and the chirp mass. The chirp mass is actually what will most easily be derived from the frequency of the gravitational wave detection. So that's often one of the first things. And then from that, we want to calculate distribution of ejector quantities. So the main one there is the mass ejecta, but also other things relating to the equation of state. And then there's light curves. Often what we're concerned about here, mainly if we're going to be talking about reporting quantities, is going to be the peak magnitude, because we care, are we going to be able to actually see this with something like ZTF? Are we actually going to be able to go find this out here, or is it too faint? And then sky maps. Where do we look in the sky? And that's what we'll be working on today a bunch. We'll talk a lot more about that later. So how do we handle these detections? So there's this package called GW Celery, and that's what we work with, and it handles the LIGO and Virgo alerts. So this is automated follow-up analysis, sky localization, parameter estimation, and source classification. It sends out these automated alerts because we got to act fast to find these transients. Astronomers everywhere will start looking for them if it's a possible good event. And that's something that we need to act fast, because these transients are only on the, maybe up to a week, but really if you want to see the bright stuff, a couple days, a few days. So a lot of times we have to act very, very fast. So one of the things I work with is a package called EM-Bright, and we're incorporating, and that will be used by GW Celery for alerts. I'm just going to give an example of kind of data products that are used in a real world scenario here. So one of the products is HAS-NS, and that is one that we work with. And it's essentially, is there a neutron star in the merger, right? Because as I've talked about, we care about BNS and NSBH. If it's a BBH, we're not going to be finding a kilonova for it. There are plenty of people that do care about them, but we're talking about follow-up opportunities, right? We need there to be a neutron star. And so this HAS-NS, it's essentially defined from 0 to 1. You can think of it as probability or expected, whether or not we're going to be able to find a neutron star. We do the same thing for HAS-Remnant. Is there mass ejected? Is there a mass ejecta? So if we have a NSBH, we may not see a significant amount of mass ejecta. And right now, we're defining this HAS-Remnant in our case as a system has a remnant if it has mass ejecta greater than 10 to the minus 3 solar masses. So it has to be a significant amount of mass ejected. And then we make any estimate of the ejected mass, and then we report the 10th, 50th, and 90th percentiles of the light curves, specifically the peak magnitude. Just a little bit to show how this process works. Here is a diagram of how we do this. So we start with the component mass distributions. If you have M1 and M2, we take the equation of state, which we marginalize over, and we can calculate a distribution of mass ejected. So how that actually works is we'll use a variety of equation of states because we don't actually know exactly what the equation of state of a neutron star is, right? That's what we're trying to study. So if you imagine, let's say we take a component mass pair and we use 100 equation of states, we get 100 different possible mass ejected values. And then we have to take theta, a viewing angle, and phi, an opening angle, and I'll show that later. And then we can calculate the light curves. And that is, information on the magnitude and duration of the event. So here's an example of some ejected mass distributions that you could see from, this would be simulated galactic neutron star and black hole population. This would be, we're trying to estimate what would the population of neutron stars and black holes look like out there, and what could we expect to see then from mergers based on that. And you see that the NSBH, as we talked about, is going to have a much, much smaller mass ejected here, and is actually much more likely to even not even have a significant amount of mass ejected. But you can see that a couple different distributions we use for binary neutron stars, pretty similar, but they're much different. And so you're going to get much, much more mass ejected, hopefully, with these BNS cases. And so now into the light curves, which is a more interesting part of this. We can see that on top, we're going to have the BNS case, and on bottom, we're going to have the NSBH case. Again, this is for a simulated galactic population of neutron stars and black holes. In the real world scenario, we're going to get a detection, and we're going to have posterior samples. Somebody is going to estimate what do they think M1 and M2 could be, and we'll run it through, and we could get a similar plot like this for eventual and hopeful O4 detections. And so you can see an example of how we could report this. We can report the 90th, 50th percentile of these light curves. You can see what light curve corresponds to what mass ejecta and what theta. And the theta here is the inclination angle. And so that's the angle that essentially you're looking at the object. And I have a plot later. We'll explain that more, but you can imagine a kilonova with jets coming out either side. If you're looking directly at the jets, you're going to see it brighter. It's like a flashlight, right? If you point the flashlight right at your face, it's going to appear brighter if it's at an angle. So, and so you see here that we found for this population, more than 90% of the BNS ones have a significant amount of mass ejecta, meaning we're hopeful that we could see a kilonova. Obviously, depends on how close and other factors and how much mass. Whereas for the NSBH case, we were only around about 1%. So it's based on our simulations. We're, hopefully that we could see more, kilonova still from the NSBH, but this is what we found here. And you can see that obviously the BNS covers a brighter and wider range of possible light curves there. So now getting into our sky maps. And one of the packages you'll be using in the notebook a little bit later is going to be using HealPix, which I just want to give a little introduction, excuse me. It's hierarchical equal area isolatitude pixelization. What does that mean? It splits up a sky map, a surface of a sphere in this case, right, the sky, into equal size or equal area pixels. And so you'll see a couple parameters in the notebook, which you shouldn't have to play with too much, but just so you understand, it'll be n side, and that's going to determine essentially which of these colored balls we're looking at here, right? Are we looking at more pixels or less? And you can see it increasing n side going up. What does it do? It specifies the number of pixels by this formula that they define, which is 12 times n side squared, which is just how they define the number of pixels. It scales up very fast. You take a slightly bigger n side, you're gonna get many more pixels. And then one thing that you'll see in the notebook is hp.ang to pix and pix to ang, which is just converting between RA and DEC to n side and the pixels, right? We need some way to convert between how HealPi understands things, which would be the pixels and the n side, and to what we actually care about, which is position in the sky, RA and DEC, right? So that's what those do. So here's a couple of examples of actual sky maps here from simulations. These are just injected events. And so what's the main thing with the sky map? It's where can we expect to find an EM counterpart to a gravitational wave event, right? So Shreya explained to us how to triangulate those events. You remember the whole thing with the annuli and the intersection. And so that results in these sort of streaks across the sky that we can hope to find the event. And we have credible regions here in just a refresher if anyone is, forgets how this works, but if we see, we'll have this, the inner region will be the 50% credible region, meaning we're 50% sure the event falls within this region. Then we'll have the big 90% region, which means we're 90% sure that the event falls within that region. And so this, if you remember from the other talks, is what leads to the problem, right? That we have to cover often a pretty large swath of the sky, and we want to do that efficiently and effectively. And that's how we use these automated and calculated scheduling routines to search the regions of highest probability, and also to search, the most efficiently. So you go from, one region to another. And so now about finding the event. So here's an actual nice sky map of some gravitational wave events and how their different localizations on the sky look. Some events are well localized and we're able to find them, like GW 170817. As you see, compared to a lot of these other ones, it was much more well localized. And how we, how we're able to localize them depends on a variety of factors, mainly signal strength and how many detectors detect the event. So if you remember from Shreya's thing with the with triangulating the event, right? If you have more detectors, you're going to be able to narrow it down to a smaller region in the sky. And also, if you have a higher signal to noise, you're also going to be able to have a better detection and further narrow down that region. So in general, if you look at these big cases, right, this would be very hard to search for an event. So how can we improve our odds? Higher sensitivity of detectors, which we're currently upgrading, 04 will be starting soon, and then more detectors, right? So the more detectors that detect it, the better we can localize, and of course, better scheduling routines, as was brought up, because the better we can search the space, also the faster we can hopefully get lucky and find that event. So when this all works, right, GW 170817, we see we're able to localize it in the sky, search that region, and actually detect the transient. And so here's an example, and this is from actually from LIGO.SkyMap, which you'll also be working with, and it just shows how we can localize the event. You see that the different detectors, and you lead to this, the overlap of the different localization regions leads to where we expect the event to be. And you can see how we have the credible regions within there, and then the actual location of the event there, and then image there, just above the for everyone. And so it allows us to find the actual event. So this is what we're hoping to have many more of come 04. And so here's an example of a simulated 04 BNS event. And this is essentially what you'll be working with today. So this was created with the LIGO SkyMap.plot or LIGO SkyMap plot, which you'll try today. And in this case, right, we're simulating an injection. So you can think about we create an event, so we know where it actually is localized. You can actually plot, like for example, this is where the actual event is, and this is the sky map that we would see corresponding to that. Obviously, in the real world scenario, we don't know where the star is. We got to go find it. But in the simulated case, right, we do. So you'll be able to play with these sky maps today and with some of the heel pick stuff. So this is with LIGO SkyMap plot and using heel picks. So you'll be using that today. And one other fun thing that's in the works is Michael Leo Singer, who's at NASA Goddard, and I are working to add some inclination information to these sky maps. And so if you remember back to what I mentioned about the inclination angle, you see this is the inclination angle there. And for everyone on here, the theta right there. And so that is it's the angle away from, essentially the jet or the polar region that we're looking at. And this impacts the brightness of the light curves and then therefore the sky maps, right? And so currently in LIGO SkyMap, they just marginalize over the inclination angle and kind of just pick one then inclination angle and make one sky map. We have a branch in the works to include the full inclination distribution to these sky maps so that for each sky map, we could actually have 10 different sky maps for a range of each 10 inclination angles. We just make a simple grid over the cosine of the inclination angle, and we're trying to include that information so we could also report information about the inclination. And I'm going to hand it off to Emily, and she's going to get us started on the observing scenarios portion of this.
Okay, so hi everyone, I'm Emily, and I'm going to talk a little bit more about the actual simulations themselves and how we do them. So as you know, LIGO's had 3 observing runs so far. The 4th one is being planned for early next year. And our work is about getting everything ready for that. So we're simulating gravitational wave merger events, binary black hole, binary neutron star, black hole, mergers. And we do this by generating source populations with realistic distributions of masses, spins, distances, all that stuff, and running them through an algorithm which simulates these merger events and estimates the likelihood of detecting them using realistic false alarm rates and localizing them. So, and as I said, we can attempt to localize these things using sky maps, which Andrew talked about, and you'll get to try your hand at today. And after this, we generate a lot of helpful statistics, which we can make publicly available, one of which is a prediction of the merger rate, which I'll get into later. And all of this is in the hopes that we can be better equipped to detect some kilonova in the next observing run. And there are two different ways of doing this, of generating source populations, which I'll get into later, the RNP and base star inject populations methods. So this graph can look a little daunting, but basically we have rows of different merger events, binary neutron star black hole, and binary black hole coalescences. And these are the cumulative fractions of events for things like the area in the sky, the co-moving volume, the luminosity distance. And these are simulated events for O3. The thick black line is, which you can see on all these graphs, that's real O3 data, which is publicly available on the LIGO website. And the LRR prediction, which stands for Living Relativity Review, is the dotted blue line. That was a simulation done by LIGO Virgo in 2019. And as you can see, it's a little bit inconsistent with the data. It's not great. So our methods, RNP and base star inject, we're trying to correct this essentially. RNP, which is short for rates and populations, that's shown in red. And this takes into account data from previous observing runs. It essentially calculates the conditional probability of events occurring given, in this case, O1 and O2, since this is O3 simulations. And base star inject is the new method, which is shown in green. And it's a fast sky localization algorithm for modeled events. It reads the match filter time series from search pipelines and calculates posterior probability distribution over the sky location and distance of the source by using proper signal to noise thresholds for the given gravitational wave detector network. So basically, this is just saying that it takes into account sensitivity thresholds of the gravitational wave detector network and is able to calculate the probability of these events occurring in certain regions of the sky. And the RNP and base star injection methods predict similar outcomes for binary neutron star and neutron star black hole mergers. But as you can see, base star injections is pretty on the nose for most of these. All right, so a little bit more about the actual sampling methods themselves that we use. So we grouped our source populations into different types of merger events based on different mass intervals of the two objects involved. And below those intervals, you can see the number of samples for each merger event in the populations. And there's these things called mass gaps, which if you've seen that giant graph of the masses in the stellar graveyard, there's a giant gap, which there's a certain interval which we don't really detect any merger events in, and that's what's represented by these mass gaps. We don't really know what happens there. So we just take them out, and we only care about the binary neutron star, black hole, binary black hole events, which are outlined there. So as I said before, the RNP method is based on detected events, so it has an inherently high signal to noise threshold, and therefore we actually need less sample events to be confident that we can end up with some good detections. So that's why the RNP samples have significantly less samples than the base star inject samples. However, there's a drawback to this. Even though we're choosing our samples more carefully, it takes a lot more time, which if you know anything about detecting kilonova, time is everything. So here is the annual number of detections that I mentioned earlier. These are our predictions using these new methods. If we trust our simulations, which we have reason to believe that we should, these new detection rates are actually quite promising. I don't have the exact numbers on this slide, but for O3, we only predicted to detect one or so binary neutron star events. And of course, with GW 190425, no electromagnetic counterpart was found, and we have no confident kilonova detections from 03. So if we can better detect these binary neutron star merger events, then we have a better chance of overall of finding kilonova. And an increased amount of detections means a larger probability of detecting them, especially since the base star injection method is extremely fast. So this is very promising.
Right, and so as well as the number of detections, we also make predictions about what we can see in terms of the credible area and the co-moving volume. So if you talk about the 90% credible region, that'd be the region in the sky, right? This is in terms of square degrees. So this is what can we expect to see for a median event in terms of sky localization. So if you look at, for example, the BNS, it'd be about 2100 square degrees, and that would be the area that we would have to sweep in the sky in order to find this event, with ZTF. And you look, those numbers are, similar for NSBH, maybe a little bit better for VBH. And then the credible co-moving volume is a similar thing, except that would be the volume in space. And if you're familiar with co-moving volume, or you need a refresher, it's a volume that takes into account the expansion of the universe, right? So it would also expand as the universe expands. So this just gives you a region or a estimate of the region in space that you would be able to find, or we would be able to detect events, right? You think of it as a sphere around Earth with that volume that we could hopefully find events within. And then we also have a luminosity distance and sensitive volume estimate. And so this luminosity distance, again, if we're thinking about median values, this is the distance that we would expect to see events at. And then the sensitive volume, which again would be like a sphere around the Earth, the volume of which we would be able to detect events. So if you see for luminosity distance, BNS up there, going to be smaller. NSBH and BBH will be increasing, right? Because we can see larger masses there, and hopefully, therefore, a louder, you could say louder gravitational wave signal and a higher signal to noise, right? And then we go to predictions for 04 and 05, comparing base star inject on the left here, or your left, and then the RMP here on the right. And so we see essentially plots of the fraction of these events. So on the left here, we can see again the credible area in degrees on the sky, the co-moving volume, and then the luminosity distance. And you can see how those would change for 03, 04, and 05, obviously getting better as time goes on. And so, you can direct your attention mainly to the base star inject, right? That's what we hope to be the most accurate one here. And we can see again, that's just essentially a plot of what we're looking at these values there. These are just the median values from these plots. And that is all. Also, thanks to Wiseman there in the back who helped out with all these simulations. So, and if anyone has any questions, now you can go ahead and ask.